If you work in facilities management, tab, or commissioning, you will need a tool to monitor your water consumption, flow surveys, or test and balance your hydronic system. The solution is the Fuji FSC Portable Clamp-On Ultrasonic Transit Time Flow Meter. Easy to use, accurate, built to last, and economically priced. Available for purchase and rental from Instruments Direct, your ultrasonic flow meter experts.
Hello, everyone. Good afternoon, good morning, or good evening, depending on where you are today. And welcome to the second webinar in AABC's Tab Talk series. Thanks to all our members and non-members across the community for participating today. And a special shout out and thanks to Instruments Direct for supporting this webinar. I have a few Zoom notes before we get started into things. If you have questions for our speakers, please use the Q&A button in your Zoom window, not the chat box, and we will feed those questions to our speakers at the conclusion of the presentation. And you can submit questions at any time, so there's no need to wait until the end. If you have technical issues, please use the chat box to inform us and we will help you out. And today's presentation is all about the value of the testing, adjusting, and balancing process and what it provides to the building performance and project closeout. So here's a little bit about our experts today. Rebecca is the founder and president of Questions and Solutions Engineering, a consulting engineering firm committed to working with facility owners and operators worldwide to achieve high performance from their new and existing mechanical, electrical, and life safety systems. She's a nationally recognized leader in the building commissioning industry and has written a monthly column about commissioning for Engineered Systems magazine for more than 20 years. It's a great column, please check it out. Miles is also working at Questions and Solutions Engineer as a commissioning engineer. He has 12 years experience in the industry, getting his start as civil engineering officer in the Air Force, where he served in various roles overseeing the design, construction, and operation of facility mechanical systems. And since leaving active duty, he has remained on faculty at the Air Force Institute of Technology as an Air Force Reserve officer to continue teaching courses in HVAC control systems, as well as HVAC design and analysis. And then finally, Mark is here with us. He's been active in design, HVAC, and construction industry since '79. He has been a practicing designer of building systems such as HVAC, plumbing, fire protection, and building automation for several highly respected engineering firms. And while there, Mark started noticing a disconnect between the intent of design and system installations. So his interest began to turn to system quality control and commissioning, which led to the purchase of SMB of Minnesota in 2008. So without stealing any more time today, I'm going to hand it off to Rebecca to kick us off. Rebecca? And I think you might be muted.
Okay, good afternoon. I'm Rebecca Ellis. I'm a mechanical engineer and I've been working with building systems for more than 30 years. I started in design, but soon found my passion in building systems operations. Over the course of my career, I've seen building systems become more complex, efficient, and interdependent. It is no longer okay to just install equipment, piping, ductwork, and electrical conduit and expect everything to work. The secret sauce for achieving proper systems operation is balancing and controls, and these two are dependent on each other for success. Today, we're going to talk about the importance of balancing, and that will necessitate a sprinkling of controls. The testing, adjusting, and balancing process and the value it brings to building performance and successful project closeout is often overlooked and undervalued. By participating in this webinar, key construction team members who drive project schedule and project closeout will benefit from understanding some of the mechanical system tab procedures, as well as the problems that can occur if those procedures are either bypassed or impeded. We will also offer some best practices to better integrate the tab professional into the construction team. I believe we all understand that a majority of the post-construction challenges are related to building mechanical systems. Many of these can be avoided by making the most of the TAB procedures required by the project specifications. So listen up. Miles Ryan, a QSE commissioning engineer with whom I've worked for about 3 years, and Mark Cotroneo, owner of SMB Minnesota, whom I have known professionally for more than 25 years, will tag team the technical aspects of this webinar. They will cover the following topics. So we'll define the role of the TAB contractor in a construction project. We'll share our perspective on the current relatively broken state of TAB as a tool for project success. We will explain to which project team members this webinar is geared, and we'll delve into a number of technical details regarding common systems which require balancing. And finally, we will end with best practices for enhanced project success. Objectives for today's webinar. In summary, we hope to add to every participant's understanding of TAB and its importance to their project success. Mark? Now you're on mute. You're still on mute. You're still on mute.
There we go.
How about now? TAB is a quality control process by which HVAC systems and equipment performance is tested. Water and air flows are adjusted to meet the system design requirements, and finally, systems are adjusted to meet the design intent. TAB measurements provide eyes into the system that other members of the construction team typically do not have. The root causes of many system performance issues are often identified and addressed during the TAB process. If a TAB firm is not brought in ever or too late, there is often numerous fruitless efforts by others to try and identify the issues, which is costly to all involved.
So where are we today? From our perspective, as both commissioning providers and TAB contractors, it seems like TAB is considered a necessary evil to be endured. Because it is a standard specification requirement, TAB needs to be addressed during construction. However, we have seen many owners, project managers who do not emphasize the importance of balancing, and their contractors will follow suit. If the owner doesn't show an interest, neither will the contractors. A TAB contractor may come to the construction site, perform their work, and submit a report, but that report may simply go into the submittal file and not even be read. Worst case, a TAB contractor doesn't come at all and no one even notices. So if included in a project master schedule, a construction master schedule, TAB is identified typically as a one-time activity that likely doesn't have enough days allocated to it and isn't sufficiently coordinated with completion of the systems that need to be balanced. So scheduling typically does not take into account the close coordination between TAB and controls that Miles and Mark will talk about today. Finally, TAB and commissioning are often misunderstood to be the same thing. However, they are both critical elements to achieving and demonstrating proper system performance functionality. TAB is different from commissioning, and TAB is a prerequisite to successful functional performance testing, which is the culmination of the commissioning process. So as noted previously, the key construction team members who drive project schedule and project closeout will greatly benefit from understanding the common mechanical systems TAB processes, as well as the issues that can occur when those processes are bypassed or impeded. The list of intended audience members here is in order of priority of who needs to hear this presentation. Now I will hand it over to Miles and Mark for the good stuff.
All right, thanks, Rebecca. Hey everyone, I'm Miles. I work with Rebecca at Questions and Solutions. I'm a commissioning engineer. And today, for actually the bulk of this presentation, we're gonna be kind of diving into some common HVAC systems and then detailing what are the common TAB procedures performed on each of those to get all the attendees kind of up to speed with better understanding what the TAB professional is doing and why he or she is doing it. So Mark's going to help me kind of detail what those typical TAB procedures would be for these typical systems. And then after that, we'll talk about common issues often found or related to the tab process, or the tab process not being fully integrated in the construction team, or in the worst case scenario, the tab process not happening at all. So let's get started. First off, we're going to talk about a variable air volume system. So let's just do a quick system diagram discussion here to explain how a variable air volume system would typically operate. In the bottom left, you have an air handling unit. That air handling unit typically has 3 dampers associated with it. It's got an outdoor air damper, which can modulate to dictate how much outdoor air is being brought into the system for ventilation purposes. It's got a return air damper, which can modulate to dictate how much air is being recirculated back from the spaces to be reconditioned and then sent to the spaces again. And then you have an exhaust or a relief air damper that can modulate to dictate how much air is being relieved from the system. Okay, so the recirculated air and the outdoor air goes through a mixing box. They go over a filter to clean up that air. And then we have heating and cooling coils within that air handling unit that are going to be used to essentially get the discharge air or the supply air coming out of the air handling unit to some temperature. Let's just arbitrarily assume that that temperature set point is going to be 55 degrees year round. If you have 55-degree air available in the supply air duct, that's a suitable temperature to provide cooling to any of the downstream served thermal zones that are being served by this system. So let's talk about zone 1 here for a second. Let's say zone 1 is calling for cooling. We would know it's calling for cooling because the thermostat would be reading a temperature above space temperature cooling set point, and it would be calling for more cooling. So how does it call for more cooling? Well, what it would do would increase the airflow set point for the VAV box. That is this little box in blue here. The VAV box has 2 major components in it in this case. It's got a modulating damper, which can modulate to maintain the active airflow set point for that space. And it's also got a reheat coil, which can raise the temperature of that supplier going into that space if need be. So if it's calling for more cooling, we want to increase the quantity of air, that 55-degree air that's being sent into the space. The airflow set point would increase, and the damper would respond by opening a bit more. Okay, so that's zone 1. It's calling for cooling, and it's actively trying to control for cooling. Now, zone 2, also served by the same system, might be calling for heating. Maybe the space temperature is falling below space temperature heating set point, and in which case, the first step in that would be to start reducing the amount of cool air that's being sent into the space. Now, I will say that there's different ways to control VAV boxes, but I'm kind of detailing here the most conventional way. And that most conventional way would be the first step, if we're overcooling a space, would be to reduce the airflow going into the space. So reduce the airflow set point for that VAV box. You can't completely go to 0 though, because occupants in that space are going to need some ventilation air to be circulating through that space. So we might go to some minimum airflow set point. And if we're controlling on that and the space continues to overcool, well, then we'll start to raise the temperature of the air being sent into that space by modulating a control valve, which is serving the reheat coil in that respective VAV box. So the cool thing about variable air volume systems is with one air system, you can have some zones calling for heating and some zones calling for cooling and be able to satisfy all of those thermal zones. Now, as those dampers and all the respective VAV boxes are opening and closing, the static pressure in the supply air duct is going to be changing a bit. So if they all start closing because they're all satisfied and they don't need as much cooling, the pressure in the supply air duct is going to increase. If it starts to increase above a set point, well, then that information would be relayed back to the air handling unit. The air handling unit would say, geez, the pressure in the supply duct is rising above set point. That must be an indication that dampers are closing, and therefore I could probably slow this fan down because I don't need to push as much air as I'm currently pushing. And in turn, a variable frequency drive would be used to slow down that fan to track the static pressure on its respective set point. So that's a VAV system. Now I'm going to turn over to Mark to talk about some of the common tab procedures performed on such systems.
Thanks, Miles. The process starts with measuring each VAV box airflow through a duct traverse or readings of each outlet and comparing it to the BAS display. Each temp control system has a calibration procedure to follow, and which saves the K factor. Once the calibration is completed, the diffusers are read and proportioned accordingly. Once all VAV boxes have been calibrated, enough of the boxes are indexed to their max set point to match the design for airflow of the supply fan. As Miles alluded to, is that the fan isn't really sized for the total system, but just the major portion of the system. So then the airflow is measured by a duct traverse, and the VFD is set to maintain the design airflow. The return fan and VFD are then measured and set in the same manner. Many systems employ an airflow measuring station, usually in the outside air duct, that controls the outside air damper. This needs to be calibrated for site conditions. Similar to the VAV box, duct traverse is completed and the readings compared with the BAS display. An adjustment factor or gain is then input into the airflow measuring station or the BAS. The static set point in the system is set by monitoring the set point and the percent open of all the VAV boxes. By monitoring the BAS display, we're looking at all the VAV boxes, making sure that the boxes are all calling for some kind of cooling or open. Then the set point is adjusted up or down until only about 1 or 2 VAV boxes operate at 100% open position and are reading their design airflow. Miles?
Thanks, Mark. So some of the issues related to the balancing process on variable air volume systems are as follows. I'm going to just kind of pull from examples of projects we've seen in recent years. So you can have temperature control issues. We're recently, me and Rebecca are working on a project right now. It's a casino resort. And the reason we got pulled into that casino resort was for something I'll talk about a little bit later here. But while I was there, some of the facility operators mentioned that there's some spaces that they just have really poor temperature control, and some of those spaces have a bad air movement, and they didn't know why, but there's some issues. And a quick review of the BAS, we found that an uncalibrated, or actually in a couple of cases, a failed airflow sensor in those VAV boxes the VAV box was basically thinking that it had like 1,000 CFM of air, which was well over set point. It started restricting down. Eventually that VAV box damper was at 0% open. There was no airflow, but it was thinking there was airflow. So therefore no airflow was provided to the space, no temperature control could be done in the space. So that is something that you could bring in a tab contractor to help verify that sensor has failed, or if during the previous construction project, which wasn't too long ago in this particular building, had that been done, maybe that would have been identified back then if it's been an issue for that long. Another project would be like uneven flow distribution within a thermal zone. So a project I was working on in a hospital about 2 years ago, it was a scan room for like a MRI machine or something to that effect. And there was an equipment room just off of that. And I was sitting in the equipment room, which they had been occupied and had been using for several weeks prior to me actually performing a commissioning process on there. And I was just getting cold air dumped on me and I was just freezing. And as it turned out, they hadn't actually finished the tab work prior to us coming in and functionally testing, but we kind of had a unique timeline that we had to meet there. And we don't like to do functional performance testing prior to tab, but sometimes it happens. But ultimately, the tab contractor, once they came in there, they were able to make some adjustments to the diffusers and more evenly distribute the cool air that's coming out of the diffusers within the space. But up until that point, the person who was sitting at that workstation that I was sitting at that day was quite uncomfortable. Tuning issues. So, you know, when a tab firm, tab professional comes in and they make adjustments, they might identify some various issues that result in drastically different water flows or airflows through a system than was previously being realized. So an example of this is we're working right now on a high-rise residential project, and it's a complete gut job of all the mechanical systems for the most part. They're reutilizing some existing ductwork on the makeup air unit, but for the most part, it's a complete gut job. And one of the makeup air units serving one of the towers had been operating probably since May timeframe. And the controls contractor, very good contractor, spent a lot of time working with control sequences because they were pretty sophisticated because there was no glycol in this particular system for reasons I won't get into, but that resulted in us having very complicated control sequences to protect those coils against freezing during all different situations. And he spent a lot of time tuning all of the control loops and making sure that everything worked seamlessly during every possible scenario it could encounter. And the whole time he was raising his hand saying, why isn't Tab out here to finish this job? Let's get Tab out there. And they weren't being brought in. They weren't being brought in. They were finally brought in December. And then when they were brought in December, they found a bunch of obstructions in the ductwork that resulted in a giant increase in flow from the makeup air unit. They had adjusted some things on the hydronic side, which changed a lot of the pressure characteristics of the hydronic system. And really, it threw off all of the tuning of those control loops that the temperature controls contractor had spent so much time in the previous months doing, and you had to come back and redo a lot of that work. So bringing the tab contractor in far too late in this case really created a bunch of fruitless efforts on his part up until that point. Building pressure issues can be a major issue, and those are often realized prior to tab being brought in. And if you got a building where tab was never brought in, you're probably going to have building pressure issues. Going back to that casino project I was talking about, me and Rebecca originally got brought in because they were having two major issues. In the summer, excessive humidity within all of the resort, right? The casino, the attached hotel, common spaces, way too much humidity. Now in the winter, they're also getting very big drafts of cold air coming deep into the space. And they brought us in there to take a look at the ventilation systems to figure out what was the cause of this. And it was actually fairly easy to put our finger on. They had probably roughly 30 rooftop units in this system. And those rooftop units were supposed to provide the fresh air to the space. So even when it's really cold out, and some of our testing, it was negative 10 degrees out there, you'd still want to be bringing in a minimum amount of outdoor air to meet the ventilation requirements of the space, as well as to meet like the makeup air requirements for any exhaust systems. Well, all of these rooftop units had their dampers set to 0% open during these very cold times. So we were not bringing in any cold outdoor air into the space, but all of the auxiliary exhaust systems were operating. So the building was being pulled excessively negative. So that resulted in a lot of unconditioned humid air in the summer being brought in, and it also resulted in very cold drafts being brought in the winter. So for those of you on the webinar today, a lot of you, this might make sense when I say I went to every exterior door in that whole entire complex and I measured how negatively pressurized that building was. And best case scenario, I found it negatively pressurized at negative 0.07 inch water gauge, and worst case scenario was negative 0.16 inch water gauge negative pressure. So had they brought in a tab contractor when they installed all these rooftop units and set up these rooftop units to have the appropriate minimum amount of outdoor air, such building pressure issues probably would not have occurred. Some more issues. Oftentimes the static pressure set point, that right here that the fan is controlling to, is way too high. And if it's way too high, you might have all of the dampers in the VAV boxes pinched down way too much, and that might create some noise further down into the occupied space. Or you might have, within a particular zone, you might have an unbalanced system where all of the air is coming out of one of the diffusers and the other three have negligible amounts coming out of it. And in that case, out of that diffuser, it could rattle. It might be pushing higher airflow than desired, and it could create some noise issues. Other issues that might occur would be energy issues. So I previously was talking about this high-rise residential project we're working on right now, where the tab contractor didn't come in until December, even though the system was up and running since the previous May. Well, when they came in, what they found is in one of the main ducts of the system, it was an existing duct that they reutilized. And what they found is that there was internal insulation lining inside that duct. Some of it had broken away, flipped up, and was basically creating a huge blockage in the system. So once the tab contractors, or the tab firm came in there, and they have eyes into the system that a lot of the other people on the construction team just don't have, right? They were able to identify there's some sort of obstruction going on there. They looked further, they found this insulation had failed, and they got that addressed. But up until that point, there was some energy issues, right? That fan was working harder than it needed to meet the airflow requirements of the space. All right, so during the tab process, as Mark kind of talked about, there's a lot of set points that need to be determined by the tab professional and then relayed to the temperature controls contractor. And a lot of times that information, and I'm talking to the tab professionals on the call now, a lot of the times we see that information is not clearly defined in that final consolidated tab report. That information has to be documented in the tab report. Additionally, it needs to be relayed to the controls contractor so they can take those values and make those the default values for the set point on the automation system. And we do this because as the building moves into its occupancy phase, building operators, for various reasons, they have to make adjustments to the system. Now, an unknowing building operator might make inappropriate adjustments to the system, and then a few years later, they have to bring in a consultant, a retro commissioning team to come in and get the building back up to snuff. And oftentimes what we find is the set points are drastically different than what they were set up to be. And sometimes we don't have the information to know exactly what those optimum set points were determined because the tab report was either never filed, or if it was filed, it didn't have that information clearly displayed. So that kind of goes along with, don't give building operators control of these systems until they've been properly trained on the control system and what set points and what set point adjustments would be acceptable and which adjustments would not be acceptable. So along those lines, there's opportunities for information to be lost by the automation system if it crashes, and the tab professional is often very instrumental in getting that information back to them. So I'll let Mark kind of talk to that last one, the software updates gone wrong.
Thanks, Miles. Yes, we've had some issues in the past where the control system is updated and the K factors of the VAV boxes are lost. So when that happens, the system returns to its default K factors and thus makes the system unbalanced. The calibration process then needs to be redone and to get the boxes to perform per design. Boxes are kind of dumb out of the box, so they just need somebody to tell them this is what your range is. So if those K factors, along the lines of what Miles said, if the K factors are actually documented, then that's an easier and faster task. Another item is the critical path scheduling. For successful and timely project completion, critical path scheduling needs to be followed. The temperature control system needs to be somewhat complete in order for TAB to progress in a timely manner. The VAV boxes need to be under control and mapped to the BAS. The air handling units and exhaust fans need to be connected to the BAS so that they can be turned on and off and dampers manipulated. If the temperature control is not working ahead of TAB, it will cause delay in closing out the project.
All right. Yeah, thanks. So let's kind of transition a little bit into some common hydronic systems. We'll do a quick overview of how these systems are arranged and typically operate. And then I'm going to turn it back over to Mark to talk about some of the common tab procedures seen on those systems. So here you have a primary only variable speed hydronic system. So it's a hot water system. And when we say primary only, we mean all of the water that's flowing through the primary piece of equipment, boiler in this case, all that water is also being sent out to the spaces, to the loads in the building, right? It's all one big path there. All right, so on a primary only system, on this one in particular, if it's a variable speed system, meaning this pump can slow down and speed up to meet the flow requirements of the served loads. So let's talk through that. So each load, each heating coil or fin tube radiation, what have you, is going to have an associated control valve. Now, on a system like this, most of those control valves are going to be two-way control valves. So these two-way control valves modulate to maintain, to meet the heating requirements, the requests from this particular heating coil. All right. So if this particular heating coil is satisfied or it's being overheated, its respective thermostat or control is going to tell this valve to start to modulate close. As it modulates close, what's that going to do to differential pressure in the system? Well, the differential pressure in the system, that is the difference between the main supply pipe and the main return pipe, is going to start to build. And we're going to measure that differential pressure. And when it starts to build and rise above a set point, that's an indication that, hey, control valves in the system must be closing. Therefore, the flow requirements are being reduced. Therefore, this VFD can slow down this pump, and we can find some pump energy savings along the way. So that's how a variable speed system works. A primary secondary system is a little bit different, but these are very common. They've been installed for years in many applications. They're still being designed and installed. And I'm not going to go into all the nuances of a primary secondary system, but I will say there are primary pumps associated with primary equipment, chillers in this case, and primary pumps typically operate at a constant speed. When they turn on, if this left-hand chiller turns on, its associated primary pump turns on, and it's pushing flow at a design flow. It's not modulating the flow through that chiller, it's pushing flow at a design flow. Okay, the secondary pumps though are a little bit different. They operate kind of like what I was talking about before. They're going to slow down and speed up to maintain a differential pressure set point somewhere out in the system, measured across the loads out there. All right, so let's talk about how does the tab professional, what does he do to make sure that those primary pumps associated with the chiller in this case are meeting their design flow requirements?
For a constant volume primary pump, we would verify that all control valves are open first and foremost. Then we would verify that the gauges are installed in the correct location to gain a measurement, which is directly at the inlet and the outlet of the pump. If they are in the correct locations, the discharge valve will be slowly closed and the gauge read to establish the shutoff head. This process verifies the size of the installed impeller. Starting with the shutoff head that was measured, a new curve is drawn for the pump, new flow curve. Then the discharge valve is opened, the inlet and discharge gauge is read, and the difference in their value is plotted to intersect on the new pump curve. If the flow is too high, the triple duty valve or balancing valve is closed to create pressure and bring the pump to design flow.
All right, and how about if there's a variable speed drive on those primary pumps? Can instead of using a triple duty valve, would you be adjusting the speed of that pump to bring down the flow?
If there was, yes. If there was a VFD, yes, well, that's what we would do, right?
All right. How about on the secondary or the variable speed?
Variable, right. For a variable volume secondary pump, we would start by indexing all the control valves in the system to fully open. Then go through the process of establishing the shutoff head and dynamic head by plotting on a curve. If the system employs calibrated balancing valves, each one is then systemically adjusted to provide the design water flow at each user. After all the valves are set, the dynamic pressure of the pump will need to be remeasured and plotted on the pump curve to read the pump flow. And the VFD is then adjusted to achieve design flow, total design flow. If the system employs automatic flow limiting devices, auto flow valves, once the shutoff and dynamic heads values are measured and plotted on the pump curve, the VFD is adjusted to provide the design flow. And then each valve's differential pressure should be measured to verify that it falls within the design parameters of the valve. We would recommend installing the cartridges in the autoflow valves after flushing and cleaning of the system to minimize the chance of plugging the valve, which will slow the process down. After all the balancing valves are measured and set, enough control valves are indexed full open to match the flow of the design flow of the pump. And the BAS display is monitored and differential pressure set point reset down until only one or two valves are 100% open and maintain room set point. The final set point is then documented in the report.
All right. Thanks, Mark. So some of the issues often related to the tab process or the tab process being brought in too late or the tab process not being completed at all would be temperature control issues with an unbalanced system. So a building I'm working in right now, a few years back, our firm got brought into that building because none of the units, a high-rise residential, none of the units on the bottom floors were ever getting any heat out of their fin tube radiation, but everyone on the top floors was fine. And what it was is they didn't install any balancing valves in any of the fin tube radiation. And it just happened that the top floors was kind of the path of least resistance. So they always had adequate flow available when they wanted it at their fin tube radiation, and the bottom floor suffered. So our recommendation at the time was to install balancing valves to make sure everyone got their fair share of flow. And we gave some heat to the people who bought condos on the bottom of that building. Now we're back in the building because 3 years later they had installed, auto flow limiting valves, which is essentially, Mark talked about this, but it's a kind of balancing valve that basically, if there's adequate pressure in the system, it's going to internally modulate itself to limit the amount of flow that could ever go through a coil, so you're not stealing flow from your neighbors. However, in recent years, that particular facility has not done any treatment of their water. They don't have any side stream filters. They haven't been doing any chemical treatment of their water. It's gotten quite dirty, and now we're having a bunch of these cartridges get clogged. And now some units are not getting any flow. Other use, we had a couple of examples where we're actually leaking out of those valves. And now we're back in the building, and we're addressing cleaning up that water in the system so we can get back to operate well like it has the 3 years prior to this winter. All right. Some other issues commonly identified is too high of a differential pressure set point. So the tab process is typically going to determine what's the appropriate set point, the differential pressure set point that pump should be controlling to. Right? If you have a calibrated balancing valve and you have way too high of a set point, you might have some loads that are having way too much flow going through them. And that can create noise. It can have excessive pipe velocities, which can be damaging to pipes, especially copper pipes. It can also create cavitation at some zone piping devices, such as strainers and things of that nature. Also, it's a big energy waste. If a pump is working far harder than it needs to meet the heating or flow requirements of that system, you're wasting energy. Now, an example of having an excessive differential pressure set point for a system that employed auto flow limiting valves is something I recently encountered. I came to a building, and basically they had those auto flow limiting valves installed on all of their coils. However, it was a pretty mild day, and I went into the mechanical room and I noticed that the pump was operating at full speed. It was operating at 60 hertz. And I kind of just thought to myself, like, that seems odd, but we were doing functional testing of the system. I knew I was going to get to it eventually and figure out why. And sure enough, when I got there, I found that the differential pressure set point that pump was controlling to was 30 pounds differential, which for the tab professionals, you're probably thinking that seems a little high. Maybe the rest of you are not familiar with it. It might mean nothing to you, but I will tell you it's an alarmingly high. You don't really see set points that high. But I called the tab guy on the phone. He had been there the previous week, and I said, what's going on here? It's set to 30 pounds. Is that what you used? I'm like, what was the process you did when you came and balanced the system? And he said, I went out to all of the valves, all of the auto flow limiting valves, and what they did is they basically plugged their system in and they verified that the differential pressure across those valves is being met. And if appropriate pressure is being met, that means that you can, I guess, trust that the valve is controlling to its selected flow rate. And he did that at all the valves, and he's like, yeah, they were all getting the flow that they required. And I'm like, yeah, but clearly they're just pinching down a ton because we have too much differential pressure in the system. Why did you end up on a 30 pounds differential pressure set point? And he's like, well, that's what they were operating when I got there, and I basically just came in and verified that they were getting the flows they need to. I was like, well, we need you to come back because we need to back that set point down to an appropriate value so this pump isn't running at full tilt all year long just to have these auto flow limiting valves throttle back and dissipate that pressure. So he did come back. We landed on a differential pressure set point of 8 pounds that we're operating at now. And in turn, we're not wasting so much pump energy. All right. Next slide. All right, this is like one of my pet peeves, and that, oh, I got excited, moved ahead. So one of my pet peeves is missing balancing valves in the bypass. So back to this schematic here. On a variable speed system, most of the control valves at the loads are going to be two-way control valves, because when they start to close flow, that's going to drive up the differential pressure, and then the pump will know to slow down. It's important that they're all two-way control valves, or most of them. However, oftentimes you're going to have one or a couple three-way control valves in the system, because if none of these loads were calling for flow, you have to give a path for the pump to push flow through. So you have to give them this bypass pipe right here. So if this three-way control valve closes its port to load 3 because there's no reheating requirements, then we still have a path for the water to flow through. All right. Oftentimes, the balancing valve right here in this bypass leg is not installed. It's often missed by the designer. I've seen a lot of cases where the design firm is using copy and paste details for the last 40 years and they're putting in the design package, and it's been missing that balancing valve for years. And then there's also cases when the mechanical contractors decide not to install it, even though it might have been spec'd to install. So let me give you an example of why this creates controllability issues. So this is probably last spring. Yes, definitely it was last spring. It was at a hospital. They installed a hot water system very similar to what we see here. There's actually only 3 loads on that whole system. And one of the loads had a three-way control valve. And in like the 4 months prior, the spring of last year, the 4 months prior to me coming in to do functional testing, I was hearing rumblings from the construction team, and I did a little bit of trend review remotely as well from the automation system, that the 2 pumps, there was not just one, there's 2 pumps, supposed to operate in a lead leg sequence, meaning that, you know, when there was high flow requirements, both pumps are going to be running. On milder days, swing seasons, probably just one pump is going to be running, could meet the needs of the system. Well, both pumps were running for like 4 months straight at 60 hertz, full tilt. And before I went into my functional testing, I was scratching my head at why that was the case. Well, they were running at full tilt because they could not meet the differential pressure set point. And I had my suspicions, but when I went out there for functional testing, we confirmed that they had never installed the balancing valve in the bypass leg. So what had happened was this particular coil, this is a heating coil on an air handling unit. It was spring. It didn't have much heating requirements. It was actually on a dual duct system, in the hot deck on a dual duct system. So it had some heating requirements, but not much. Therefore, this port was closing a bit. This port was opening, but as soon as you open the port to the bypass, if you don't have a balancing valve there, that's a short circuit. So now all the water was short circuiting around that coil. The differential pressure was dropping when you'd expect it to increase when you're having a loss in heating requirements. And because it dropped there, the pumps responded just the opposite of what we'd expect them to do. They sped up. The lead pump told the lag pump to turn on as well. Then they both sped up together. And then they got to 60 hertz and they stayed there for 4 months. And the frustrating thing is we brought this to the team, and there was probably 4 meetings between, you know, the owner, the design firm, us, the commissioning providers, and the contractor, trying to talk him into like why this was needed. And also at the end of the day, the design called for it. It was needed. They did install it, and I was there. They installed it, we balanced it, and that system has been off running just fine ever since. So if you're a design engineer, don't forget the balancing valve in the bypass. If you're a contractor, even if the design doesn't call for it, put in an RFI. There should be a balancing valve in the bypass. And if you're tab or commissioning provider, look out for that, because it might be a reason your system's not operating the way you expect it to be. All right. One other example of this, if you have a cooling tower, and you have a cold climate, cold weather operations, and you have a bypass with a 3-way diverting valve, is very common. In this bypass leg, you also have to have a balancing valve. I almost never see it, and it definitely creates issues. However, most people don't witness this issue until you get to cold weather operations, because that's when this valve starts modulating, and that's when the system can get really unstable. You start tripping out chillers. And when you trip out a chiller in cold weather, now you're risking freezing water up in the cooling tower. It's just a whole host of nightmares that we've ran into in recent winters because of a lack of balancing valve placed in this line right here. All right, I'll get off my soapbox about balancing valves in the bypass line. Couple final things. Flow obstructions can be identified by the tab provider because they have eyes in the system that a lot of us don't have, right? So bring them in at the appropriate time in the construction process. We have a project right now where it's a middle school I'm working on, and you know, in true fashion for a school project, that new rooftop unit got installed and started up about 2 days before school started. Tab couldn't get out there to do their work. We couldn't get out there to do the functional performance testing. But luckily they did bring in tab early enough before it got real cold, and they found that there was an obstruction in the existing hot water system, which was preventing all hot water from going to that rooftop unit, which could have in turn froze that downstream cooling coil once the weather turned in December. And like before, in these systems, these hydronic systems, tab is responsible for determining what the appropriate set points are for a lot of the set points used in the automation system. That information has to be documented in a tab report, but it also has to be relayed onto the controls contractor. Now on the hydronic side of things, I have a good example. We got brought in about 2 years ago into a museum, and what had happened is the previous building automation system, the previous control system had crashed. And it got completely gutted and replaced by contractors installing a completely new system. And after they installed the new system, they started having humidity concerns, humidity issues, too high of humidity in the collection spaces of that museum. And they kind of brought us in there to look at that issue and a couple other issues to get it sorted out. And when we looked at the system, we said, well, geez, it looks like the serving air handling unit is actively trying to dehumidify. The cooling valve is open completely, but we're not really seeing a big temperature drop in the air at the air handling unit. We're also not seeing the chilled water pumps speed up much. So we started asking the question, well, what's the appropriate set point for the chilled water pumps? We asked the contractor who installed the new control system, and they said, you know, we're just using this value. We had nothing to work with because the previous control system went blank. It was completely dark. We had nothing to work with. We couldn't find any tab reports. Tab wasn't within our scope to bring in tab for this project. Luckily, our firm 7 years prior had done a retro commissioning in this facility, and we had screenshots on our computers that showed what the appropriate set point should be. So it was actually a fairly quick fix. Once we figured out the appropriate set point, put it in there, pump sped up, dehumidification started to happen, and as far as I know, it's not been an issue ever since. All right, these next two things, low fill pressure and airlock, I'm going to turn over to Mark to talk a little bit about.
Yeah, many times the control valves are closed during the flushing of the system. And when the flushing is complete, the valves are open and air is bled out. If the system is not filled to take care of that air in the coils, then the pump experiences low inlet pressure, which affects the pump's ability to develop system pressure. Another issue is airlocks. If the coils or any user has the air not bled out of the coil, they can become airlocked. The water is trying to push through the air, and it can't do that, and thus it impedes the water flow, and then you can't get any heat transfer out of that.
All right. So let's transition to something that a type of system you typically don't associate with tab. At least a lot of people don't. And that would be like domestic hot water recirculating system. So just a quick overview of what do we mean by domestic hot water recirculating system? Well, we have a water heater here that is creating like hot water, maybe 140 degrees, 130 degrees, sending it out into this pipe. But now we'll create a loop. We have a piping loop with a pump on it, a recirculating pump, that basically makes sure we have hot water available in this piping loop at all times, because we'll have takeoffs from that piping loop to the various fixtures, the various showers, the various faucets. And we want all of the users of those fixtures to have hot water in a relatively short time frame. So that's the whole concept behind a recirculating system on a hot water system. Now, if you have something as simple as this, you probably don't have many issues with it. And probably as tab professionals, you probably never looked at something this simple, right? But once you start getting into the high-rise residential units and other high-rise buildings, there might be multiple paths for the domestic hot water to flow through, right? So from each one of these 3 risers here, you want to have hot water constantly circulating through each of these 3 risers because they all have respective takeoffs going to different fixtures serving different units within that facility. Now, riser 1 is kind of the path of least resistance. So more flow is going to go through the path of least resistance unless you put on balancing valves on each of these paths of flow to make sure that they all get their fair share of flow and all of the different fixtures throughout the facility are having hot water available on demand in a reasonable time frame. I'm going to turn over to Rebecca to talk about some of the issues we see with domestic hot water recirculating systems. Oh, actually, I jumped the gun. Let me turn over to Mark to talk about the SAP procedures that would be associated with that.
We're going to skip me. The process to balance the domestic water system is similar to the hydronic system, measuring the shut-off head of the pump and then the dynamic head of the pump and plot it on a curve. Then we would go through each recirculating balancing valve and set to the required flow for that branch. Auto flow valves are verified by measuring the required differential pressure. Sometimes thermal balancing valves are used on the system. This does not allow for any measurement or adjustment. If that is the case, the pump the speed is set, and with the hope that the owner is happy with the operation of the system.
You're on mute, Rebecca.
Miles is the only one who's got the mute button figured out. All right, so what I think real things. Sometimes there are no balancing valves included in the design documents. Sometimes domestic hot water balancing directions are not provided in the project specifications. And most times the tab contractor doesn't even consider balancing the domestic water as part of their job. So this is definitely a highly reflected loop, but it's a really important one, especially in multifamily housing. You know, whether it's dorms or apartments or condos, people notice right away if they're not getting hot water when they try to take a shower. And it's not something they can put off for a month or 2 or wait until the contractors figure it out. They get really vocal really fast. So we're often called into buildings that are pretty new, where owners aren't getting the hot water when and where they need it. We find flow is going, the hot water is being maintained to the units closest to the pump, and no flow to the units furthest from the pump. That's so easy to figure out if you just kind of plot out where the complaints are coming from. We also see many times pumps are insufficiently sized to push the water through the piping. The domestic systems are called open systems, and it's a different pumping strategy or design that you have to think about. You not only have to pump through the pipe, which creates friction loss and pressure drop, you oftentimes have to pump it to the tops of a tall building. And if you don't account for all that hydrostatic pressure in that column of water as you're trying to push the water back up to the top of the building, it's just not going to flow. It will simply just stop, and there'll be no flow anywhere. And then Mark alluded to these thermal balancing valves. They are controlled. They're balancing valves in the position shown in Miles' schematic, and they're pretty much just 2-position valves. If the water temperature entering the valves is above a certain hot enough, they will actually close because they're sensing there's hot water in that riser or in that pipe. But as soon as it cools down, the valve opens, will start to open maybe at 110 degrees Fahrenheit. And that once it opens, it'll start letting the hot water flow until the riser fills up with hot water again. Those are very popular these days. and they're great for contractors because they work usually at the beginning. If you have enough pump, if you don't have enough pump to push through the system, no type of balancing valve will work, including these. But over time, they will fail. They're mechanical devices and they will fail and you'll start having problems. And as Mark alluded to, there's no way of figuring out where the failures have occurred. You can't measure the flow across these devices. All you can do is really go up with an IR gun and measure the temperature of the pipe to see if they're actually working. So lots of stuff that, rides under the radar for construction projects and contractors that if you're not taking care of them at the end of the project, may very well come back to you in a few years if they start having problems with domestic hot water delivery.
One of the reasons that the plumbing system is not done is a lot of times it's not even specified by the design engineer to do that, other than the circulating pump. Also, there's a lot of the tab companies will shy away from plugging into the domestic recirculating balancing valves because of the potential risk of contamination of the system. We mitigate that by using a dedicated water meter for domestic system, which is disinfected prior or after each use. You could also use a ultrasonic water meter, which doesn't plug into the valves themselves, but measures the flow through a pipe, which again, you're not plugging into the valve, so you're not taking that risk on. So, Rebecca.
That's it. Let's see. So I think we promised to close out some best control. Critical for making sure the systems perform as required. TAB needs controls to manipulate the systems as part of the balancing process, and controls need TAB to understand what the correct set points are for control sequences. And TAB controls are often a tag team effort. Controls need to be complete to a certain extent before TAB can be performed, and then controls cannot be completed until TAB is complete and the control system set points determined. So it's not as simple as saying you got to finish controls and then you have to do TAB. It's an iterative process between the two of them. And the sooner those two subcontractors start talking to each other, the better the process will be. Mechanical contractors and design engineers need to read the TAB reports and understand what issues were discovered that need to be corrected. You're spending good money on the TAB contractor and they're finding really good stuff. And if you don't do anything about it, it's a waste. So as commissioning professionals, we regularly see problems documented in the TAB report that no one takes responsibility for correcting. So that's an issue, because that's going to come back and bite you later when they manifest themselves in problems the owner is going to discover. Then the commissioning process should confirm that the set points in the control system were determined by the TAB process and not just estimated by the controls contractor. So if not, there will be an action item in the commissioning action list for the TAB contractor and controls contractor to coordinate with each other like they should have done in the first place. And then finally, due to a perceived conflict of interest in having the TAB contractor working as a subcontractor to the mechanical contractor, many owners are pursuing alternative TAB procurement arrangements. So we've seen test and balance under the general contractor instead of the mechanical contractor. We've seen test and balance under the construction manager. We've seen test and balance under commissioning professional, and sometimes, especially with big institutions, test and balance directly to the owner. So there are different ways of engaging TAB and maybe giving them a more prominent role in the project, something that reflects the importance of their work on the overall project success. And finally, this is a special plug for Miles. Don't forget the balancing valve in the three-way valve bypass line. So as we close, Miles, Mark, and I trust that we have added to your understanding of TAB and its importance to your project success. Now we'd like to open to questions.
Okay, thank you all. So let's jump into the questions. We have a decent amount come through, about 8 or 9 to get through. And if anyone else has questions, now's the time. So let's jump into things. First one, an attendee asked, should I use the auto flow to verify water flow to terminal unit or through the coil?
Mark, I think that's, and you're on mute.
Well, if there's an auto flow in the system, I would, as long as you have the differential pressure at the auto flow, that is a calibrated piece of equipment and is supposed to provide the correct flow. So I would use just the auto flow.
Perfect. Next question. Can you address when and how during a project you suggest balancing domestic hot water circulation systems before or after chlorinating the system for portable use? How do you balance those systems when already in use?
Sam, you garbled a little bit.
Sorry about that.
In the second half of the question, it didn't catch that.
Second half of the question, before or after chlorinating the system for potable use, or it might be portable or portable use. How do you balance those systems when already in use?
I would say at the end, but Mark, how would you answer that?
I was going to say probably at the end, and that's where that's why we use the a dedicated meter, chlorinated and disinfected. Before, I'm not sure how much water. I guess they will probably flush the system through, and we normally wouldn't want to read through or do any measurements while they're flushing the system. So once it's ready to work, or once it's ready to go into service, I think that's where when we would want to do it.
And I think the second part of the question, Rebecca, was how do you do it in existing buildings? And I guess we could talk to a project we're working right now, trying to rebalance domestic hot water recirculating system in an existing building. The answer is very painfully, especially when a lot of the balancing valves are located in inaccessible locations or within the units themselves. It becomes a very time-intensive, costly process to have to go back and rebalance it because it wasn't properly balanced and set up to begin with. I mean, it'd be a lot easier if you do it before they move in.
Yeah, other than the accessibility issues, balancing an existing building shouldn't be any different than balancing it in the first place, as long as you have all the correct balancing devices. And that's usually what we're missing in existing buildings. We might not have balancing valves. We might not have ports for measuring pressure across pumps. That data, I mean, those missing things are a big clue to the fact that it was never balanced in the first place, because the raw materials required for balancing just aren't there. So in this building that Miles is referencing, we've had to add balancing valves, replace pumps, all kinds of stuff to get it working again.
Okay. This next question is sort of a two-part one. One attendee asked, what is your opinion on doing functional performance tests ahead of TAB? Many commissioning providers will not go there without a final stamped TAB report. And then I want to note that a different attendee independently said, as a commissioning agent, we think requesting the final TAB report approved by the engineer of record before functional testing is a good practice. Do you agree?
I'll answer that. I think it's a good practice. It's not a very practical practice. If you wait until the final balance report, you've probably way down the project schedule and probably into occupancy. As a kind of compromise position, we want to have the balancing report, or even the balancing report associated with the system that's being commissioned. or being tested. We want to see that, and we want to see what things the tab contractors found, and then we will make a decision whether those items are going to impact functional performance testing or not. And if we think those issues need to be corrected before we test, that's what we'll say. If they're kind of non-critical issues, we'll go ahead and schedule the testing. But to the first question, we definitely believe it's important to have tab done before commissioning functional testing. And that's because there's a job to do, and tab has had a lot longer in buildings than commissioning. And that commissioning is kind of an add-on, after tab, with controls and the complexity of building sequences and the interaction of integration between systems and equipment and systems and systems. That's kind of why commissioning is there, but the need for tab has never changed. And we don't want commissioning to take the place of tab or be responsible for identifying things the tab contractor will identify if they just did their work before us. So we're very adamant about having tab done first, because there are a lot of good stuff that they will find that if we went right into functional testing, we'd find them at least manifestations of those tab issues during testing, and they're still going to need to be corrected. So.
Thank you, Rebecca. On one of the hydronic systems slides, Miles, one person asked about the ABVs that were clogged. Did they give a strainer?
No, they did not have strainers at the individual devices. They had strainers in the system. I mean, they had strainers upstream of the pumps. They had strainers it was on a district heat, so it was upstream of the heat exchanger for the facility. They did not have side stream filtration, which is a recommendation currently, and they had a chemical pot feeder to do chemical treatment. Just no record of them doing it in the last few years.
Great. So next question, what is your process for reconciling deficiencies in the tab report to tab verification as it relates to functional performance testing? What sort of timeline have you experienced when it comes to getting the final tab report?
That's a lot of questions in there. Getting the final tab report doesn't really the issue, as long as, well, because we did not look at the final tab report, initial tab report, we're less concerned about getting the final one. We certainly want to know it's delivered, but we're more interested in making sure that the issues found in the preliminary tab report are corrected. And we look at them, and they are said to be corrected, and we'll start our testing. And we'll do the proof that those things have been corrected if the commissioning process doesn't naturally do it on its own. So as far as delivery of the final tab report, it is one of those common things that is always on the project closeout list. So it comes in, and it's not like we're waiting months and months for it typically. It's not a difficult thing, especially these days when the tab contractors are doing so much electronically, and tab reports are being generated automatically. It's not like they have a backlog of all this paperwork to do back in the office. Would you say that's fair, Mark?
Yes, we've got, certainly from our point of view, we've got our time to a final report or to a report to a commissioning agent from probably 2 weeks to maybe a couple of days. So yeah, we've got it done. So yeah.
Right, that's helped a lot. And Sam, there was a question in there about something in there about tab verification.
Yes, they were
And
asking.
I'm not, yeah.
Do you want me to restate it?
Yes.
So they're asking, what is your process for reconciling deficiencies in the tab report to tab verification as it relates to functional performance testing?
So tab verification, some projects, the commissioning agent scope involves actually going out with the tab contractor and spot checking some of the readings. I'd say in our experience, that's less than 50% of the projects. So that's not a big piece of the commissioning process from our perspective. It's something I think owners ask for if they feel like they've had issues with tab reports in the past. But for the most part, we haven't. The tab verification process has been just an exercise to go through. I don't think it's been a place where we found a lot of deficiencies. So if the question might have been, if there are issues in the preliminary tab reports, how do we verify that they're corrected? We do verify they're corrected either through the functional testing process, if the deficiencies will show up as being corrected there, or we just wait until that final tab report where the tab contractor confirms that that issue's been resolved.
Okay, thank you. So one attendee asked if anyone can discuss how PT plugs or gauge cocks need to be installed at each coil, and that many copy and paste details incorrectly indicate a thermometer well between the test port and the coil.
Mark?
It would be nice to have PT plugs at the coils, at each individual coils. Quite honestly, if there's a balancing valve there, that's what we'll use. We wouldn't use these other means unless there's no other way to measure it. So it's belts and suspenders probably, so we would just use the balancing valve, and we would rather have the balancing valve. That's a calibrated piece of equipment that should probably be used.
But if you are going to put teeth plugs there to measure, theoretically, to be able to measure the differential pressure across the coil, they should be the first things in and out of the coil, right? Not have any thermometer wells or anything else in the way.
Certainly, the location of them, yeah, you should be the very first in and out, yes.
Mm-hmm.
So next question, one attendee asked, is bypass balancing valve balanced for same water flow as the balancing valve for the corresponding load?
Yeah, I can answer that. Okay, so on a system like this, this one right here, it does not necessarily, if you went full flow to the coil, right, you're going to have a certain pressure drop across the coil. Now, if it was a constant speed system where they had three-way control valves on every coil, then yes, you would match the pressure drop across the balancing valve to the pressure drop across the coil. However, in this scenario, on a variable speed system, when you got just like one or just a couple three-way control valves, essentially, you're going to want to adjust this guy. You're going to want to basically close all of the control valves to the loads and adjust that guy to make sure that you're meeting your minimum flow requirements, whether that's for your like steam converter or your boiler or whatever would be like that limiting factor at the lowest differential pressure set point that you could realize. And then you probably want to put a little safety factor on there as well. So oftentimes what I'm saying on a variable speed system like this guy's cranked down even more to have even greater pressure drop across it than its respective coil, because really it's just there for a path of flow in case if everything else shuts off in the system. So it's a little bit different technique depending on variable speed versus constant speed hydronic systems. When it
but
comes
Miles,
to,
wouldn't it the opposite potentially be true as well? I mean, if the flow through that load 3, when it's balanced, is not the minimum flow required for that boiler, let's say, then that bypass might have to be balanced to a lower pressure drop in order to maintain the minimum flow to the boiler.
Oh, did I say it back? I guess I'm thinking of it as, okay, I'm not sure if I might have said it backwards, but basically you're measuring this guy for flow. So if you have design flow of like, let's just say 100, let's say 100 GPM for make it easy. So if you got 100 GPM here, but the minimum flow for your primary piece of equipment is 50, then you would put all these valves closed, this control valve to full bypass, and you would set that to 60, give yourself a little cushion.
Right.
So I might have misspoke the first time.
No, you said that, that's what you said. But I'm saying if the boiler minimum flow is 150, then you would set that valve for 150.
Oh yeah, yep. I guess that could be, that could be a case. And then also, I mean, if the boiler's minimum is 150, it's very likely that you have multiple bypass lines out in the system, either multiple three-way control valves or a separate dedicated bypass line with a control valve on it. And then when it comes to putting a balancing valve there, I mean, like, I think all the ASHRAE guidance, like all the journal articles and like the chilled water plant design guide that's out there, they're going to say, Matt, the pressure drop across here should be equal to the pressure associated with a column of water, the height of the cooling tower. And that's for controllability reasons there, because there now, if you're measuring, condenser water supply temperature going into the chiller down here, and you're trying to use this guy to essentially send some of the water to the cooling tower, divert some of it, so your mixed temperature lands on your condenser water supply temperature set point. You don't want this to be no balancing valve, because then you're going to short circuit water there. It's going to become very unstable, and this valve is going to start hunting. The moment this valve starts to try to control for temperature, very rarely do you see this done well if there's not a balancing valve there. It's just a controllability issue.
Yeah, thanks, Miles. So, comment from a tab guy. They're asking, and I know this might have been touched upon already, what about quality controls? There's been a large lack of them in hopes that tab would catch things.
Good question. Where are they? Where's the quality control?
Yeah.
I want someone on a mechanical or general contractor to answer that one.
Yeah, there
because
should be
we hear the same thing for
process.
commissioning. Yeah.
Yeah, each process should have its own quality control, and we'd like to think that that's the case. But when it comes down to the end of the project, it really, as far as operationally is concerned, anyway, the tab certainly picks up a lot of the first things that have issues. Things like missing dampers, missing valves, that kind of thing in order to do the operation. And then commissioning comes back, and then they can really find out that a lot of the control isn't there either. So, yes, it is an issue on projects, and hopefully everybody's working on their own, not just waiting for tab or commissioning to pick up all the issues.
Okay, this one's from the person that asked the bypassing balancing valve question. They're asking, is the balancing valve in the bypass also required in chilled water systems?
Yes, I mean, if you're talking at a coil, like in this scenario right here, if this was all blue pipe and this is a chilled water system with a chiller and cooling coils, yes, kind of like you'd often see like one or a couple three-way control valves with an associated bypass pipe, and the exact same concept applies there, that you would have a balancing valve on that to make sure you're always meeting minimum flow requirements for the system.
Thanks, Miles. Another attendee is asking, since the systems are getting very complicated, maybe it's a good idea to begin commissioning the systems before the tab to ensure the units are operating correctly and working with proper sequence of operation. Do you agree?
I think
possibly, then commissioning becomes part of the iterative process and becomes more expensive to start with. But Mark, what were you going to say?
Well, depends on what you mean by commissioning. The two processes really dovetail into the whole finishing the project and making the system work well. Again, with the scheduling, we can't put the cart before the horse. So we can't tell if we're going to check that air handling unit to make sure that it does what it's supposed to do, a lot of times the volume of that unit needs to be verified or checked or set in order for that piece of equipment to work correctly. So, and like you said, then it's another person with a temperature control that would need to be at every step of the way. And it's and again, it's not a linear process. We go back and forth a couple of times to different pieces of equipment in order to make them work. And it would be another person to do it. I think if there's like on the tab process, if we have temperature control, say at something like 75% completed, and then we can start similarly, like I know you do, Rebecca, is when the tab process is about 75 to 80% complete, then you can start your process. You don't have to wait till the very end, but you do have to have so much of the volumes set and working so that the controls can work, or so that the system works correctly.
Yeah, and I liked what you said. It kind of depends on what you call commissioning, because if we can combine that with the quality control question, I would say absolutely the controls should be commissioned by the controls contractor. You know, point-to-point checkout, testing the sequences of operation, fine-tuning the sequences of operation. That would be ideal. I mean, they should be doing it themselves. I mean, third-party commissioning is really verification that has happened at the end of the project. But within the project flow, if the controls contractor gets the sequences working and fine-tuned, it definitely should make the tab contractors' work easier and maybe more valuable.
And to allude to what they're saying about sequences getting more and more complicated, what we detailed today was some of like the more conventional tab processes for more conventional systems. And like, yeah, what's conventional these days, right? Like it seems like every building's got some like unique thing where you have to scratch your head and be like, okay, for that to work correctly, you're going to have tab come in and take that measurement, which they're probably not tracking or they're not used to. So a lot of times some of our more complicated systems with unconventional tab processes, we don't necessarily do functional testing before tab, and then tab comes and then we do it all over again. But we interject ourselves into the process by often calling, hey, we need to have like a tab integration meeting, and temperature controls has to be there. And the commissioning provider who's been involved with helping refine the sequence of operation ever since the design phase, we're going to be there and we're going to say, let's talk through this. Like, what information does the tab provider have to find out that's kind of unique that they're probably not tracking, and then in turn provide it to the temperature controls contractor. So there's oftentimes in our projects where, you know, we will budget for that. We will budget for like some of these like tab coordination meetings to make sure that everyone's tracking right. So we get it right, or as close as we can to right the first time around. So when we show up for functional performance testing, we don't say, oh, tab didn't do that, tab didn't do this, this is a mess, I can't test anything. So that's kind of on those really complicated ones. That's kind of some of the ways we've worked around through that, I guess.
Great. We have so many great questions coming in. I know we're running over, so I just want to answer a few more and then we can end things for the day. So one attendee commented that in his opinion, outside air in one of these schematics presented earlier in the presentation is not to modulate, nor are outside airflow stations needed. What are your thoughts on that?
Well, there's many different ways to do outdoor airflow control. And the conventional way would be minimum outdoor airflow control. So like if the economizer is disabled in hot, humid days, or if like it's really cold outside and the economizer kind of goes to zero, the conventional way would just be set a minimum damper position there. And just assume that you're going to meet your design, you know, minimum requirements for ventilation all the times. Well, with variable speed systems, that's just not the case, because depending on how fast that fan is running, even if that damper is 30% open, if that fan's at 60 hertz or if that fan's at 45 hertz, you don't know what your flow exactly is going through there. So there are more sophisticated ways to control outdoor airflow. One of those would be to install an airflow measuring station in the outdoor air duct, which has its own host of issues that can kind of come out of that. But in that case, when you have an airflow measuring station, one way to do it would be to modulate the outdoor air damper. Another way would be to have the outdoor air damper fully open and you modulate the return damper. There's many different ways to control outdoor airflow, but to say that there's no sequences out there where you modulate the outdoor air damper, I mean, that's not correct because I've seen it many of times. So.
Okay. Last question. How do you accurately measure the flow through a chiller when 30 coils obtain control valves off the DDC system and 100 coils only obtain two-way control valves with the remote room thermostats? How can you make sure all the valves are open, non-modulating to get full flow?
I'm assuming that you're talking about just a primary system through the whole system, not primary, secondary. Well, that's a little tougher. We could, what we normally do is would read across the chiller bundles to make sure that the pressure is correct. That's also done with the chiller manufacturer or the startup person. We could do that. We would want to open up as many valves as we can in order to set the pump speed. And if we don't get them all open, then we would certainly calculate the speed of the fan to what they need to. If we know that it's only going to be 50% of the flow or something like that, then we know that we need to speed up the fan accordingly in order to set the differential pressure. But through the chiller itself, probably reading across the bundles would do it.
Okay, thank you so much, Mark. Miles, do you mind flipping to the end of the presentation to the final slide there?
Yeah, sorry.
Thank you all for your wonderful questions. Thank you to our experts who came here today and gave us their time. If you enjoyed this presentation, the Tab Talk webinar series continues in May with a talk on pressure independent valve technology with one of our industry partners, and then also a certified AABC professional. There's the scan to register right there. And while you're here, the reason we're waiting until May for the next webinar is because throughout April, with collaboration with the Energy Management Association and the AABC Commissioning Group, we're helping to present CX Energy Virtual, which features 15 live and pre-recorded technical sessions. It's free to all AABC members, so be sure to register. Thank you all. Stay safe, stay healthy, and have a good afternoon, night, evening, morning, wherever you are. Thank you all.
Thank you.
Thank you.